Hello, welcome back. So today in this video we will be talking about a particular motion that is very common in many of the problems we encounter, and that is the motion of a projectile. So let's first of all define what we mean by this. We have intuitive definition of what a projectile might be, but let's define it. So a projectile motion projectile is a motion that is only affected by gravity. Motion only what did I write? Influenced by gravity. So you can imagine there is a particle. There's gravitational force acting on it like this. This force creates an acceleration downward, A, which we know in close distances, close heights to the surface of Earth, it's relatively constant. And it is downward with, let me remove the sign. It is the gravitational acceleration of the Earth. We use letter G. And that one remains relatively constant. At least with our engineering practice, we can assume it is constant. And because of that, the motion often looks like a curve. And you throw it from here with some initial launch condition. Maybe your ball goes up and then comes down, hits another place. So this is important that a projectile, if it is only influenced by gravity, it will have very nice, well-defined properties that we can study. And that is what we will do today. So just as a reminder, I have a few reminders on the right-hand side. And I want to draw your attention to. So we are dealing with a curved path. So in this situation, we need to go back and use our curved equations. And because I know gravity is only downward and it remains constant, it also means there is no acceleration in the other directions. So A equals 0 in that direction, A equals 0 in that direction, and I only have acceleration in the vertical direction. Let's call this axis Z. And this situation fits very nicely with the rectangular frame equation. If I want to remind you, acceleration, velocity, and position, they can all be decomposed along the axis of x, y, and z. And essentially, along any of these axes, we can study the motion independently. For instance, if I know acceleration along any of these axes, I can work backward and calculate velocities and positions. So this projectile motion is very well suited for rectangular coordinate frame definitions. As a background note, if you have other forces such as aerodynamic forces, then the direction of those forces are influenced by the path, and then you will not have this nice constant acceleration only in one direction. Everything changes, and probably in those conditions, rectangular frame is no longer the best choice. But as long as we have only gravity, we have only acceleration in vertical direction, and this separation provided by the rectangular frame works very well. Another thing I want to remind you of are the equations, the solution to equation of motion. When the acceleration is constant, we know in any direction, any rectilinear motion or along any path, when acceleration is constant, we can use such equations to find the velocities and acceleration given the known constant acceleration. So let's combine these two ideas, rectangular frame and constant acceleration, to find the motion of a projectile. So let me clean up here a little, draw a nicer figure. And one other thing to remember, doesn't matter which direction we have our projectile, the entire path will always be in a single plane. So we can always work with a 2D version of essentially 2D projection of the motion on a single plane. So let's go and call these axes X and Y. At some point, I have my projectile, maybe at some initial position, X naught and Y naught. And I launch this projectile with some initial velocity V. And we want to know where exactly the ball goes. So what we can do is decompose the motion along the X and Y axis. We don't have a third dimension here, so just X and Y would suffice. And what I can do, I can, at any intermediate point, such as this one, I can find the velocity, this velocity vector. No, that's not a good point. Let me go back a bit further down, like here. I have my velocity vector. Let's call this V naught, so we don't confuse it with velocity as it changes. I will have two components of the velocity, Vx and Vy. And at any time, I also have the acceleration that is g downward, and the acceleration always remains constant. A equals g equals constant. So I want to write the equations along the two axes. Let's start with the horizontal axis because that is easier. So acceleration along x-axis, I know at any time is 0 because acceleration is always vertical. So there is never a horizontal component to acceleration. And because of that, using these equations, I can immediately see that Vx at any time is going to be V naught at x. So velocity along the horizontal direction always remains the same. And the horizontal is the horizontal component of V naught x, V naught y. And because of this, I can also go one step further, find x, which always is going to be x naught plus V naught xt. Just applying the equation of position, knowing that velocity is constant. So let me move this here slightly nicer. And these are the x component of the motion. So that was easy. X component, where do I write it? X. Now let's look at y. Y is equally easy, but there's slightly more terms in the equations. We know acceleration along the y is always minus g, minus because it's downward. So it's in the opposite y direction as I have chosen here. Because of that, I can calculate velocity along the y to be velocity, initial velocity, minus gt. And finally, position along the y is initial height plus the initial velocity, v naught y t, minus 1/2 gt squared. And these are the equations for the y component of the motion. And if you want to go back and work with vectorial form, your position is going to be this x I plus y j. You can substitute these values. Velocity vx, the same way we calculated, I plus vy j. Let me write it down. X is going to be v naught x t. Let me write it this way. I like it more this way. X naught plus v naught xt in I direction plus y naught plus v naught yt plus 1/2 what did I want to write? Minus 1/2 minus 1/2 gt squared in j direction. Velocities vx naught or v naught x. What was my v naught x? V naught x I plus v naught y minus gt j. And finally acceleration equals 0I minus g j. And these are the vectorial form. One last thing, maybe two last things, I don't know, one last thing. Sometimes we, if you know the vectorial form, you can always calculate the speed, which is norm of this velocity vector, is going to be square root of this squared plus that squared, v naught x squared plus v naught y plus minus gt squared. So you can calculate the speed as a function of time, which increases and then decreases. And one last thing, in the y direction, often we don't know the time, but we want to find, for instance, maximum height or similar situation. We can use the time independent formula. So delta y, or y minus y naught, times 2g. Let me write it better. Minus 2g y minus y naught equals v squared minus v naught squared, both of these along the y direction. And yeah, I think I'm out of space, so that is all good for now. Here, for instance, when the height, you want to find the maximum height of a projectile, you know that by definition maximum height happens when there is no further velocity component in vertical directions. So this vy square would be 0. Knowing the initial vertical launch velocity, you can find the maximum height. I think that is all I wanted to say here. I cannot remember anything else. There is one more video. We can talk about the shape of the motion. And that would be it for projectile motion. So I'll see you in the next video.